easy. Next one is this work calculation. All right, let me make sure that I don't have anything besides work calculation. It's correct. Work calculation, we start with a uniform force is used and non-uniform force is used and things like that. So let's start with this was two things, right? Density and mass is one application in physics, and second one, the work calculation. That's the end of section 6 application. So I'd like to spend some time about the concept of work calculation. The definition is straightforward, and I'd like to explain what that definition is, because it's not geometry, it's not as straightforward as the density. It is a little weird definition to me. So I'd like to explain a bit. Why did they define it like this? My ultimate answer is that they actually created this notion to convey this conservation of energy concept nicely. This definition, mathematical formulation, built into this conservation of energy idea, right? That's why they define it like this. So here's some first example I'd like to go through. A bid on a straight wire. It's very hard. It's not bent. It's like rod, but it has a hole in there, you can imagine, just like necklace and beads in there, things like that. That's the situation. So I'm going to consider these two things, mainly to understand what this work calculation is about. So here is work calculation. What is work in physics? Here is a rod there, wire, and there's a bid in there. And this is the direction of a gravitational force. And this the angle of the direction of a force in the wire is a perfect 90 degree, and it is in the bit is right in there. All right, I'm not touching it, only the gravity is acting on it. So let me ask this two question there. I haven't defined the meaning of work in physics, but I'm just appealing to your everyday notion of a work. So it is staying there, not moving at all, and you ask the question, is any work done by gravity? Yeah, so my first answer was no. Gravity didn't do anything to that, but I'm sure it's pulling it down, right? Here's one thing. Newton tried to make this force situation as the following. If this is our interest, we'd like to ignore everything else is what's going on out there. All he cares about, what kind of force is acting on it. Gravity is acting on it in there, right? But it's not moving at all. Therefore, he assumed that something else is acting on it so that the forces cancel out, and it is staying in exactly the same position. So the wire usually doesn't create any forces, but Newton had to assume that wire creates the opposite force. So they cancel and not moving at all. So the bit is the only thing that will glow in the dark. If you turn it off, if it's not moving at all, and Newton conclude that whatever happened to that, the total exerted force to that point is 0. That's why it's not moving, right? So wire creates that force there too. So it's not this work done by gravity, but there's work done by wire. You can think about all sorts of crazy things like that. So maybe you can accept that, oh, gravity didn't do anything. It's just staying there, nothing. But if there's a heavy rock and you push that like for an hour, and you will say, God, I did a lot of work on that one. It just didn't move. That's exactly the same thing, right? So you will say that I did a lot of work, and why'd you say that no work is done? So it's the same thing as a gravity. So that's one confusion you can possibly have. So let's see if I'm actually moving this one. All right? And there's a little greasy, so it is actually no friction at all. When you push that, no friction at all. If you apply constant force to that one, it begins to move, right? How would you describe the motion of this one? If you constantly push it, apply the force with the hand to move it from position A to position B in there. Accelerating, that's the key point, right? Accelerating. If you keep pushing it, and it's supposed to accelerate, right? So that's definitely it moved, right? If that's the only thing that will go in the dark, your hand, you cannot see it. Your point move from A to B, some work must be done. Moving at a constant speed, right? Accelerating speed, but definitely work some is done. So it's just a notion. I'm not quantifying it yet. And I think what I was trying to do there is try to look at the different sources of force. But total force is what really matters, right? But sometimes we look at the different sources of forces acting on that. So, so you also think about the total work done moving A to B, because different forces are acting on it. In my hand, the gravity and wires acting against it, all sorts of things, right? Too confusing. What is the total work done on that? You can think about that. So those are the first notion, but it's not good enough. So this is a little puzzling part. If nothing is moving, we cannot see hand or wire or anything, only that bit. If it is not moving, you conclude the total force exerted on that is 0. That's why it's not moving. Another confusing part is that it's actually moving through the wire. We don't know if there's a wire. It's just moving along it, but it's not accelerating. If hand is pushing with a harder and harder, the same force all the time, it's supposed to accelerate, right? Supposed to accelerate. But if it is not accelerating, then you should conclude that no total force is zero total force is exerted, right? If there's some total force, a positive amount of total, it's going to accelerate. So it's very important. No motion and no change in the velocity in physics is the same thing, because relativistically, you don't know where you are in the universe. You don't know who's moving or what, right? So that's why it's the same thing. All right. So here's the thing. If something is moving along, you cannot conclude some work is done. Think about rock moving through the universe with no gravity whatsoever. Nobody's pushing anything. It's moving, right? But no work is done, right? It's just moving. Right, it's a total versus independent sources. That's what you're thinking. The total, if it is moving at a constant speed, the total force exerted is a 0. Therefore, there's no work is done to that part. But if the velocity is changing, but it could be the case. Here's the following situation. Why I say that it may be. Suppose that wire is thick enough and very rough. Therefore, there's a significant amount of frictions involved, right? Then you cannot, if you push the constant force in there, you're dealing with the amount of friction, right? Just the right amount to deal with the friction. So if I push that just the right amount with the friction, how would you describe the motion of a bid? So here, now I'm saying lots of friction, right? I'm pushing it so that it's exactly dealing with the friction. Total amount of force exerted to that, what would you say? Friction will work against it here, opposite direction. That's very difficult to see why that works like that. But all that matters is in the direction of the motion. If I'm pushing it to that one, whatever the stress tensor is working out with the surface of the bead and the wire, all that matters is how much of the force is acting against that's the friction you feel. I'm just dealing with that exact amount, right? So total force acting on that bead is 0. So what would you describe about the velocity of this one? Change or no change? No change. So bead will move in a constant speed because I'm just dealing with the friction, just right amount. Now I'm going in here. If somebody's working on that bead, do you think? My hand is working on that bead, right? So there's some work done. But motion is a constant velocity motion. So total work exerted on that force is a 0, so you should say total work done to that motion is a 0. My hand is pushing forward, some work, friction is working against it. These two work is cancel each other and giving you the total work 0. But if the velocity is changing, you can conclude that definitely something is pushing and work is done. If it is not changing the velocity, you don't know if it is just rock passing through the no gravity zone in the universe, or I'm pushing and dealing with some frictions. The motion itself, the velocity itself, is not going to tell you what is the behind the scene. Does that make sense? All right. But going back to the pushing the rock situation, I'd like to say, will force applied to longer period of time does not really what they care about in work in physics, right? And I think it's definitely something that you have to think about, but why not? is because they want this work definition in physics for conservation of energy, especially this kinetic energy and potential energy, and put them together. All in that, what they require is something that's got to move. If a bit is in the wire not moving, there's nothing to talk about in work in the physics. It's just a zero force. It have to move, and we want to relate with the motion. So that's what they wanted to do here. If it is a motion, to encounter one variable calculus, it better be straight so that we can do one variable calculus. So into the direction of motion, how much the forces applied to that direction is what they wanted to think about. Work done along the direction of the motion by whatever the source that you're in. It could be my hand, it could be the gravity, whatever. And it is a constant force applied. How long, not how long time, but the distance of this motion. It doesn't matter how fast it's moving. It is about your force applied, constant force applied, and to the distance and multiplying. That is their notion. If you define it like this, some magic happens, although it's very, very simple definition. F is constant. If it is not the real gravity here, for example, is the component of gravity that is in the direction of the motion. So F times D is W. That is the definition of work. When F is what? Constant force. W is F times D. So here is what I was talking about. If it is not in the same direction, gravity is always pulling it down, but your little slanting side, and then you have to think about exactly what force is applied there. So if actual force is F and the direction, how much the force is applied to that direction is decomposed, and so that it becomes F times cosine theta. So let me explain that part. And this Y part, if you can explain to yourself why this is working like this, that's very good. But it's something to think about. Usually physicists just give it to you, never have a chance to think about why that is so, but you have to think about it why that is the case. So let's say F is applied to that direction. This is the direction of a force, and we're actually moving to that direction. That direction there, right? So this is the magnitude of a force. Okay, even though I represent it with a line, F is not a line. That's why it's something difficult to understand, right? F is not really a line, but I'm using as if it is a triangle. This is the angle theta. If F is not a force but length of a line, what would you be this side in here? If you apply the trigonometry, that's exactly F times the cosine theta. Okay? But that makes sense with the triangle, but F is not a triangle. It's abstract, quantity that we're associating. But they're claiming it works exactly like the triangle. So if actually gravity is applying to that direction, and if you're moving along this direction, what your feel of gravity to that direction just this much. For example, if the wire is here and the bit is there, the gravity is working this direction exactly, right? So what is the angle between these two things? A 90 degree. And I was saying F times the cosine of 90 degree is the force that is acting along that direction. So what is the cosine 90 degree? It's 0. So it's a 0 force is applied to that direction. That's why it's not moving. It's just standing there, not moving at all. Make sense? So that's the decomposition. I'm not explaining why, but that's what they say, and that must probably correct. So here's our first example, already very difficult enough. So you have to pay close attention to this one. But it can be fun. Let me first explain the whole problem first. We're going to release a ball at the 3, 2 position. So here is our xy plane. Here's 1 and 2 and 3 and 1 and 2. That's 3, 2. That's where the ball is. And we're going to release that ball along the path because of the gravity is going to go down, and that's the 2 curves. So y equals x over 2, the slope 1/2, right? Over 2, so that slope 1/2 goes like this. next part is connected. If you plug in x equals 2, you get 1, x equals 2, you get 2 minus 1, 1. So they're same position, slope 1, and at that position, so it goes up like that. So if you release the ball and you're going to roll down, it's going to probably bump a little bit because of the sudden traction. But let's suppose that was really heavy enough, so it didn't kind of toss it, really always stick to the floor and roll down in here. Okay? So I didn't do anything, I just released it and something else did the work. It moved, it worked, right? So what did the work? Gravity, right? Gravity did the work. So that's what we're calculating. Gravity, apply the forces there all the time until it reaches that point, and that's what gravity did. Alright, so let's look at this part here, straight enough. Would you believe that constant forces apply to along that direction? Yeah, because it's a straight line, it is so. So gravity, so here's the thing. Gravity going down by force G, 9.8. No, meter squared, meter second squared. Can't I get that one right? So this is the side in there, right? Do you know the angle that it is it is moving that direction, right? Because it's pulling it that. So what is the angle there? It was a slope 1. So maybe you have to look at this triangle. That was 1 unit. That was 1 unit. Do you believe that? So 1, 1, 45 degree, right? So that was a cosine 45 degree. But next one, we don't know the angle. Because 1 and 2, it is not some known angle. So I'm just going to call that one theta 1. So the method we do here still applies to the next part. What we need is that this force here, F1. What is F1? F1 is not the same as G. Somewhere in the middle, right? G and 0, right? But it's not F times G. It's Fg is a G times what? Cosine of that angle theta 1. That's what they're saying. If you can calculate cosine theta out of this triangle, and that you have calculated. So if that's a theta 1, what is a cosine theta 1, you think? We need to know hypotenuse, right? What is the hypotenuse? Root 2. So what is a cosine theta 1? Adjacent divided by hypotenuse, right? 1 over root 2. So we calculated that. F1 times 1 over root 2. The force that is pulling down along that path is the gravitational force times 1 over root 2. Smaller, right? Definitely smaller. That's how much you actually feel it. That's how much it's exerted. So do you think it is accelerating in here or moving in a constant speed along that path 1? Accelerating is always pushing, not by full G, but a little bit smaller amount into pushing along the way. Okay? So constant force applied to that path, how much work is done? Work 1, that's work done along that path, is the force, not F1, I'm sorry about this, F1. This is supposed to be what? G. That is F1 there. So F1 times D1. That D1 is this distance here, right? We already calculated. What was it? Square root of 2, right? So what is F1? Is G divided by root 2 times root 2. That is root 2 here. Is that right? 1 over root 2. It's the same thing as a G. So that's how much work is done from here to there. Does that make sense? Let's do W2. What is W2? Work done from here to there by the gravity. Right. But it is a slightly different angle. So let's do this pattern here. Let me use this shorter length. This is G. That's how much is force is represented by length. And what is this angle here? Theta 2, right? And we want this force F2. What is force F2? G times cosine of theta 2, correct? Right. Here, what is the length of this side? This side here is a 2. That side here is 1. These are length of this path. Not really related to G, but that's the magic, that the G works just like this one. What is the length here? Square root of 5, Pythagorean theorem. So what is your cosine theta 2? 1 over root 5, right? Yeah. So let's do that. F2 is how much force is exerted along that direction, coming from the gravity, and multiply by distance d2, which is root 5. So here is g divided by root 5 times root 5, right? So the magnitude of that work is g. I forgot to even introduce the unit. I think they call it joule. Newton times meter. Newton times meter. F is the Newton, that's the dimension, multiplied by meter, and that's the 1 joule. So we have g joule, right? So altogether, W1 plus W2 is a 2g joule. Is the work done by the gravity along it like that. Does that make sense? All right, here's a conservation part. You probably noticed that's a lot simpler than I thought. When you enter cosine theta, you thought, wow, that's going to be a little bit ugly. But it was really clean, the 2g, right? But you decided to drop the ball straight down to that position there, right? Then what is the distance here? 2 meters, right? What is the force that's constantly applied to that? G itself. So it's 2 times g. It is a W3, right? Work done by the gravity from that to all the way down straight is 2g as well. W3. Something is the same, right? So that is a part of this idea inside potential energy change, that it's kinetic energy change and things like that. Here's a challenging question. Anyway, this one is definitely equal, and it doesn't matter what kind of complicated path you go through, and this calculus is going to be exactly the same. So for example, if you have straight down path versus some parabola passes, it's not like straight line like that, and then a work done by the gravity, maybe you have to introduce more of a straight path with a 100 path in between, and if you calculate it in that fashion, and you can show that work done by the straight path along more segmented paths, they're all the same thing. So that is the little glimpse to the conservation of energy part in there. All right. So let me just mention this real quick because I already said that with the friction part. Work required to move it from A to B. Think about that moving that wire along with a lot of friction in that wire. And think about the minimum work is required. You can really push hard, then you applied excessive force to move it from A to B, right? Then it can be more work. But if you're just dealing with the minimum force, minimum constant force to deal with the friction, that's the minimum work you to move that bit from point A to B. So that could be most of the time what they're asking in the book. Work required to move it from A to B. Then you think about what is it that the source of a force that is working against? Friction, or is it gravity? If you have to lift the ball from the bottom to up, right? Then gravity is working against you. If there's nothing against you, so here's one trick question before I let you go. On that wire in the bead, here going back to that, this is really oily, so you don't feel a fraction at all. And you have to move this one from here to there. The question, what is the minimum work required to push that to that? Approach is 0 is a more realistic, and straightforward answer is a 0. Because once you push that very short period of time, very short distance, just gently like this, and then let that one go, so you really apply the force to 0.00 millimeter. Once you push that, that guy will just keep traveling. You don't need to push that anymore because no other force is acting against it. So your force is applied very, very small distance, so work is almost 0, like Evan was trying to say. So minimum work required to move that one to that is nearly zero. If you have to say something, it's just a zero, right? Because of that. Nothing, there's no force is acting against the direction, then the minimum work required is a zero. So usually the problem that you will see is that you have to identify the source of force that acting against it, like spring system. When you're stretching it, when you're compressing it, there is a force coming out of spring system. When you're lifting it, you're working against the gravity. When you're pushing it on the floor, you're dealing with the friction that is really due to the gravity, right? So those, you actually calculate that, and you take the opposite. That's the amount you have to deal with that. With all that, if you're dealing with just the right amount, how you describe the motion of this thing that you're working on? The velocity of that never changes. It's always a constant velocity, right? Because the total force exerted cancel becomes zero. So total force is zero. There's no change of velocity. So work required problem is talking about that kind of work. As you push it such that this thing moves in a constant velocity. Sorry about the delay. I'll see you on